My name is Griebel, third-year Ph.D. candidate in the Department of Chemistry and Biochemistry. I work in the Jeffrey Pyun Research Group. We focus mainly on polymers and organic synthesis and related to polymers. My specific research is devoted to sulfur utilization in a new way to make polymers and taking the use of sulfur to make new novel materials out of them. There's a dirty little secret that most Americans don't know about associated when they drive to and from work or to the grocery, or they take a bus or a train. All of that gasoline that comes from petroleum has sulfur in it. And in order to remove that sulfur, you need to chemically treat the petroleum so that you reduce sulfur dioxide emissions. Sulfur is so abundant in your petroleum reserves that each American contributes about 325 pounds of sulfur annually. When you multiply that by 300 million people, it becomes quite a problem. And then you multiply that again on a global scale, we have approximately 6 billion kilograms of sulfur just lying around that we have to store. But it creates an opportunity to utilize an underappreciated feedstock to make a material that we could then use for commodity uses. Specifically, I focus on batteries, next generation batteries for electric vehicles, and also on infrared optics based off of organic materials for cheaper, more accessible infrared materials. One of the big focuses in the Pyun group that we like and that drew me to the University of Arizona and the group specifically is that we try to focus on research that is not only going to be done in the lab on a small scale and then be put on the shelf once completed. We like to think of it from design to execution to application and then final delivery of a product. So the great thing about this chemistry that we've developed is it's very efficient. It uses very cheap feedstocks, and it also provides a large-scale synthesis of a material that would be useful in a battery. Current technology that's state-of-the-art in this field for next-generation batteries can produce on the order of about 1 gram of material. So you can't obviously make a very large battery with that. The advantage that we have is simple polymer synthesis that can be done on a kiloton scale if designed correctly by chemical engineers. So we like to think of it as a transition from the lab to the industry very easily because it's not a complex system. We could potentially start to alleviate problems with global warming and take care of a major waste problem of the byproduct of petroleum refining. So it'll be a new development in the academics, not only from a chemistry standpoint, but also to the industries where they start to think differently about throwing away their wastes. So in this reaction, we'll be utilizing elemental sulfur as both a solvent and a reactive species. In the molten form, sulfur can actually dissolve a number of different compounds. In this case, we'll be using a co-monomer, which we'll inject into the molten sulfur. It'll react to form a copolymer, and then all we'll be doing is cooling it down once the reaction is complete. So the sulfur in the powder form takes about 2 to 2.5 minutes to actually melt completely, and we want to utilize the completely molten form. Now that it's completely melted, what we'll do is we'll just take our comonomer, which is 1,3-diisopropionobenzene, simply add it to the molten sulfur, and then cap and let react. So now that the reaction is done, this material, which is 90% sulfur, can actually be placed in a battery architecture, and you can actually test this system just with a simple LED. By lighting up the little LED, we know the battery works, and we now have a new material for a second-generation lithium-sulfur battery.